Okay, we're going to do sections 4.4 and 4.5 kind of together. The topic here, the main topic, is rational functions. Definition: a rational function is a function of the form p of x over q of x, where p of x and q of x are polynomials and q of x is not the zero polynomial, so we know we can't divide by zero. When graphing a rational function, we must consider any vertical, horizontal, or oblique asymptotes. An asymptote is a linear boundary which a graph approaches, but it never touches. That's actually not completely true. I'll talk about that later. Many rational functions are going to have asymptotes on them. Okay, so we got to pay attention to that. Here's how to find the vertical asymptotes. A rational function, f of x equals p of x over q of x, which has to be in the lowest terms, by the way, will have a vertical asymptote at x equal k if k is a real zero of the denominator q of x. Okay, so any number that you're going to be throwing away as a result of the domain is going to create a vertical asymptote on the graph. Finding the horizontal or oblique asymptotes is quite a bit different. If the degree of p of x is less than the degree of q of x, then y equals 0 is a horizontal asymptote. Okay, if the degree of p of x equals the degree of q of x, then y equals c is a horizontal asymptote. To find the value of c, you're going to divide p of x by q of x and then disregard the remainder. If the degree of p of x is 1 more than the degree of q of x, then y equals mx plus b is an oblique asymptote. An oblique asymptote is slanted. Okay, to find the values of m and b, divide p of x and q of x and disregard the remainder. Okay, so with horizontal and oblique asymptotes, you're going to use division instead of just finding the asymptotes, and instead of stating the domain. The graphs of two basic functions, y equal 1 over x and y equal 1 over x squared, are shown below. Determine the features of each graph. I've got the graphs of y equal 1 over x and y equal 1 over x squared shown. And we're just going to answer some questions about this graph, about these individual graphs. Okay, so the first one, y equal 1 over x. The domain is a set of all x such that x is not equal to 0. Okay, so you can't divide by 0. The range is the same set. The set of all y such that y is not equal to 0. So in other words, this function heads outward in both directions and not ever going to get to the y-axis, or y equals 0. And so y cannot be 0. Okay. Now, because the function will never get to either of the two axes, we're going to have no intercepts. Okay, on the graph, and because there are no intercepts on the graph, we're going to have a vertical asymptote and a horizontal asymptote at x equals 0. Okay, and that's usually drawn with a dotted line. And I've got that on the next page, at x equals 0, and then a horizontal asymptote y equals 0, usually drawn with a dotted line. I got that on the next page, and while the graph is heading outward on both directions, it's never going to get to the axis. Okay, this function is odd because when you replace x with a negative x, you end up getting a negative in front of the function. Okay, y equals 1 over x squared. Here's the graph shown. The domain is a set of all x such that x is not equal to 0. There's a vertical asymptote at x equals 0. Okay, so the graph heads upward, and x can never be 0. Okay. The range, so when I square any number, I've always got a positive. I know x can't be 0. That's not a possible value. But x can be something greater than 0. So I'm going to have a situation where the graph covers the entire x-axis or y-axis there on both ends. Y is greater than 0. So now the fact that, and by the way, I don't have any intercepts. I don't have any. I've already said why x can't be 0 because I can't divide by 0, and y can't be 0. If y is 0, then you're saying 0 equals 1. Right? And that's not true. So y can't be 0 either. The intercepts, there are none. There's no place where the graph is going to cross or touch the coordinate axes. Okay? Even or odd, this function is even, because if I replace x with a negative x, the quantity squared, is the same as x squared. So y equals 1 over x squared, which is the same thing that I have there. Okay. Problems 1 and 2 are all about graphing using transformations, using y equals 1 over x and y equals 1 over x squared. So the first one, we're going to graph the function g of x equals 1 over x squared plus 1 by using transformations on y equals 1 over x. I have the graph of y equals 1 over x shown. Okay, and that's from the previous page there. Y equals 1 over x. X equals 0 is a vertical asymptote. Y equals 0 is a horizontal asymptote. Okay, so this graph will never cross either the two asymptotes. Now the minus 2 means that I'm going to shift to the right 2 units, and the plus 1 means I'm going to shift up 2 units. Okay, so the vertical asymptote is going to be at x equals 2. And the horizontal asymptote is going to be at y equals 1. Okay, all I'm doing is shifting the graph. I've got a couple of other points plotted there. But all I'm doing is shifting the graph twice to relocate the, the position of the graph. Okay, problem 2. Graph the function g of x equals negative 1 divided by x plus 1 squared by using transformations on y equals 1 over x squared. Okay, so here's the graph of y equals 1 over x squared that I've already got there on the previous page, this graph here. I've already said that I've got a horizontal asymptote at x equals 0, or a vertical asymptote at x equals 0, and a horizontal asymptote at y equals 0. Okay, so I've got these two lines dotted, or drawn dotted, indicating that I've got asymptotes on both of them. Okay, now the fact that I've got a negative 1 in the numerator means I'm going to flip the graph upside down, and a plus 1 means I'm going to shift the graph to the left 1. Okay, so if you imagine doing those two things with this original graph, flip the graph upside down and then shift the graph to the left 1, you end up getting this graph here. 0, negative 1, and 2, negative 1 are on the graph. And I've got the new asymptotes drawn there. Okay, to sketch the graph of any rational function f of x equals p of x over q of x, follow the 6 steps below. By the way, the majority of information is not going to be over transformations. Okay, transformations are nice to know, and but quite honestly, I think that this list of 6 steps is going to be coming more handy to us. So step 1, we're going to state the domain of f. Step 2, we're going to write the equations of the vertical asymptotes for f. There's a note. Make sure that f is in the lowest terms before identifying the vertical asymptotes. That's important. Step 3, write the equation of the horizontal or oblique asymptote for f. There's a note there. The graph of f will have either one horizontal asymptote or one oblique asymptote, or it has neither one. That's important for the graphs that we have. Problem 4, determine the points, if there are any, where the graph of f will intersect the horizontal or oblique asymptote. There's a note. A graph cannot intersect any vertical asymptote. That's important. Okay, so part 4, I guess I should be more clear with. A function may not have a vertical asymptote or a horizontal asymptote or an oblique asymptote. Okay, or it may cross a horizontal asymptote or an oblique asymptote, like right here. We end up crossing the horizontal asymptote. Okay, right here we end up crossing the horizontal asymptote. Okay, so that could happen. We're going to know the points where that happens from our work in step 4. Step 5 is to determine the intercepts for f. Okay, and then step 6 is to plot more points as needed to sketch a complete graph of f. It will usually be the case that you'll need to plot at least 2 or 3 more points in order to completely see the entire picture there for f of x. Okay, the previous work is helpful, but it usually is not enough. Okay, so for the next couple of problems, we're going to graph each rational function using the 6 steps given above. Make sure that you leave enough room there. I tried to leave you enough room for if you're writing this down. So step 3 is to graph f of x equals 2x plus 1 divided by x minus 3. Okay, so we'll go through the list of steps, and I'll just list each step on the side there. Step 1, you want to determine the domain of f, and the domain of f, it looks like all real numbers except for 3. Okay, so because we're throwing 3 away, we're going to have a vertical asymptote at x equals 3. Okay, so we get step 2 immediately. Step 3 is because the degree of the top matches the degree of the bottom, I've got a degree 1 polynomial divided by a degree 1 polynomial. Okay, so I can compare the leading coefficients. 2 over 1 is 2, and I can also divide. X minus 3 is going to go outside the division bar. 2x plus 1 is going to go underneath it. 2 is going to be a leading factor in dividing that. And so 2x minus 6 is what I'm subtracting. 2x minus 2x is 0. Negative 1 plus 6 is 7. And so I've got a remainder. I'm going to be adding the remainder. I always add the remainder. 7 divided by x plus 3, x minus 3. Okay. Now, here's another reason why it's y equals 2 is the answer. Is because if I compare the leading coefficients, I've got a 0 in front of the numerator in the top and a 1 in front of the numerator in the denominator. 0 over 1 is 0, and so y equals 0 is a horizontal asymptote. However, I'm adding 2 to that. Okay, so y equals 2 becomes a horizontal asymptote. Step 4 is to see if the graph crosses the asymptote. Okay, the way to see if the graph crosses the asymptote is to set the graph equal to the asymptote and then solve. If I multiply both sides by x minus 3, 2 times x minus 6 is what I get on the right. Subtract 2x from both sides and 1 equals negative 6. Okay, 1 does not equal negative 6. That's a false statement. So there's none. At no point do we cross or touch the coordinate axes there. Maybe I should be more clear here. So we do still have asymptotes, but the graph will never cross the asymptote. Okay. So let's go to step 5 here. The x-intercepts I need to let y be 0 and solve for x. When y is 0 and I solve for x, multiply both sides by x minus 3. 2x plus 1 equals 0, means that x is negative 1/2. And the y-intercepts, I let x be 0. When I let x be 0, I get negative 1/3 there. So two intercepts would be known on the graph. Here's 0, 1/3, and here's 0, 1/2. Okay, so after doing all that work, I only know 2 points on the graph. And I also know the asymptotes. Okay, here's y equal 2, and here's x equal 3. That's not a whole lot. Okay, so here's where step 6 comes in handy. I'm going to plot more points, and I know that the graph has to flow with the boundaries. Okay, so if x is 2, then I get 5 divided by negative 1 is negative 5. 2 negative 5 is on the graph. If y is negative 2, that should be a negative 2. Negative 2 plus 1, negative 4 plus 1 is 3, and divided by negative 5 is it should be negative 3/5, positive 3/5. So negative 2 positive 3/5 is on the graph. And the fact that I've got a kind of preview to seeing where that graph is gonna shoot at, I can go ahead and draw in the first piece there. Okay, so I'm gonna go ahead and draw in the first part, and make sure that the graph approaches the two asymptotes, but never going to get there. Okay, we said in step 4 there's no points where the graph crosses or touches the coordinate axes. Okay, and I would need to graph some more points. So if x is 4, 2 times 4 is 8, plus 1 is 9, divided by 1 is 9. If x is 5, I get 11 over 2, and so 5 11/2. And if x is 6, I get 13 divided by 3, or 4 1/3. Okay, and so I've got these points kind of shooting downward into the right, and so that would indicate that the graph heads downward and to the right, approaching these two boundaries. Now I don't have any graph down here or up here, okay, because it's got to be a function. What do we know about functions? It's got to pass the vertical line test. Okay, so you shouldn't need 5,000 points. I mean, 3 or 4 max is really all you need. I mean, really, these 2 points right here tell me the whole story. That okay, the entire graph has to be in the lower left-hand region. All you need is 1 point up here to know that the entire graph is, or the entire rest of the graph is in the upper right-hand region. Okay, I shouldn't need a ton of points, like I said, but the more points that you have, the better. The more accurate the graph will be. So consider that. Okay, we'll stop right here then.